So, today's topic is electrode potential. Electrode potential. Now, when a metal is dipped into a solution of its salts, listen, the reduced and oxidized forms of the metal come into contact. Now, we say a metal. Say, take for example, zinc metal. It's dipped into a solution of its salt, a salt of zinc. So it's going to be zinc sulfate, salt of zinc. So a metal is dipped into a solution of its salt. So if the metal is zinc, solution of its salt could be zinc sulfate, and any other solution of salt of zinc. So when a metal is dipped into a solution of its own salt, the reduced metal and the oxidized metal from either the metal dipped in the solution brings in the one part, the salt of the metal brings in the other part. So you have the oxidized and the reduced form of the metal. They come in contact. Now, example, a zinc rod, if it's dipped into a solution of zinc sulfate, which is a salt of zinc, there are two possible tendencies. Two things will possibly take place. Number one, zinc ions in the solution nearer the rod would draw electrons from the neutral zinc atom in the rod and become reduced and deposited as neutral zinc atoms. So the zinc ions present in the salt, or the salt of zinc, as zinc sulfate, which is in solution, those ones close to the rod. The rod is also a zinc, made of zinc material, zinc metal. The ions in the solution containing zinc sulfate move close to the rod, the zinc rod, and draw electrons. You know, the zinc rod is the cathode. So the cathode is covered with electrons, remember. So the ones in solution will go close and draw electrons from there, and when they gain electron, they become neutral. And when they become neutral, they are free. So they're deposited there as neutral zinc atoms. Now, number two, neutral zinc atoms in the rod go into solution as zinc ions. So since the metal, the cathode, is also made of zinc, and they are neutral already, okay, they can go into the solution also, because solution has zinc. And when they go into the solution, they are going to become ions. They are not free anymore. They are getting charges to themselves now. So they'll go into solution as zinc ions, each leaving 2 electrons behind on the metal rod. So they will lose electron. They lose those electrons. Those 2 electrons they had, zinc has 2+. Now, when they lose that electron, then you see they become oxidized, right? Good. So those are the 2 possible tendencies that could happen when you dip in a zinc rod, so a metal rod, into a solution of zinc sulfate, the solution of its salt. Okay. Now, due to the above possible tendencies, there will exist a double layer of positive zinc ions and electrons on the rod. So a potential difference will exist across these 2 layers. And when this happens, we call that potential difference electrode potential. Electrode potential, which is our topic for today. Now take note. The tendency for a neutral metal to go into solution as ions, like the zinc metal, zinc cathode, went into solution as neutral ions. The tendency for a neutral metal to go into solution as ions depend on the relative ease, how easy, the relative ease with which electrons can be removed from it, and on the available energy when these ions are hydrated. Now, we said in first term, when we're doing a periodic table and atomic properties, we mentioned ionization potential. We said is the ability or the energy required for an electron to be removed in the valence shell. Now here it comes to play again. That the tendency of neutral metal to go into solution as ions depend on, one, the ionization potential. That is the ease at which the electrons can be removed from those metal, atom, that metal. That's the ionization potential. And on the available energy when these ions are hydrated, when they are in water. When the ions are in water, what are their energies? What energy do they have? That's the hydration energy. So those two factors decide how and why and when a neutral metal can go into solution. Good. Also take note of this. The more electropositive a metal is, the greater the tendency to go into solution as ions. So, electropositive is those metals that have positive sign on top. Their charges, they have cations. But the more electropositive, more the positive, the electropositivity increase, then the greater they can go into solution as ions. So, like we say, zinc has high ionization potential, then it has a greater tendency to go into solutions as ions. And remember, when pure metals go into solution as ion, like I explained before, they are now losing the electrons that they were in the cathode as neutral elements, and so they had to lose electrons and become ions again. You understand? So loss of electron is oxidation. Now, because of this, the solution will become more concentrated with the positive ions, and the electrode becomes more negative compared with the solution because electrons are deposited on it. So as they are carrying electrons, they are moving and then depositing the electrons on the anode, the electrons become more negative. They're depositing negative things to them, and that is because the metals they had high electropositivity, so they deposit their ions. And also, a less electropositive metal in the solution of its salts will have its ions more likely to acquire electrons from its rods and then become reduced rather than being oxidized. So we take for example Cu. You have 2+, but because it's less electropositive, the Cu2+ will get reduced as they will be gaining electrons. When they gain electrons, the positivity reduces, and that means that the concentration of Cu2+ in solution will become less, and the concentration of electrons, since they are gaining those electrons, on the rod becomes less compared with the solution. The solution is gaining the electrons from the rod now, so electrons on the rod is less. Okay, so since we said that in the first one, we say that the electrodes become more negative, but in the second point we said the electrodes become less negative compared to the solution. You see the difference it's occurring. But how can we then know the standard, the measurements, the electrode potential of an electrode then? So we come to standard electrode potential. Standard electrode potential. You see the sign there, E and a kind of theta, like raised to power theta. E raised to power theta, so to say. Now, to measure the standard electrode potential of a metal in its salt solution, please don't forget, we said that a metal should be dipped into a salt or its own salts, and we said example zinc dipped into a salt of zinc sulfate, right? So you're going to be having this mentality in this topic, electrode potential, that a metal is dipped into its own salts, a solution of its salts. Like zinc metal is dipped into a solution of zinc sulfate, which is a salt of zinc. So now, please keep that mentality intact until we finish this topic. To measure the electrode or standard electrode potential of a metal in its solution, in its salt solution, standard hydrogen electrode at standard conditions. Now, what are the standard conditions? Over 1 molar ion concentration, that's concentration is 1 mole, 298 Kelvin temperature, that's equivalence of 25 degrees Celsius, and a pressure of 1.013 times 10 raised to the power 5 Newton meter, almost close to 1 atmosphere, is coupled with the salt to form an electrochemical cell. So let's read this definition, this explanation without those conditions, so you understand better. To measure the standard electrode potential of a metal in its salt solution, a standard hydrogen electrode is coupled with the salts to form an electrochemical cell. So a standard hydrogen electrode dipped in hydrogen, electrode of hydrogen the salt in question is coupled together. You understand that when we get to where the diagram is. So the standard hydrogen electrode at those conditions we don't want to mention again now is coupled like fixed with the salt we're considering to form an electrochemical cell. So what is standard electrode potential then? Standard electrode potential is the measure of the tendency of an element to form ions in solution relative to the tendency of hydrogen atoms to form ions in solution at standard conditions, which you know about. So how much an element can form ions in its solution compared to how much hydrogen atoms can form ions in solution, that is standard electrode potential. So what we are doing is we are using hydrogen atom, hydrogen electrode as datum, as a reference point. So if we can keep that one, since we keep the value for hydrogen electrode at one point, and then we compare other electrodes with them. If there is a difference, then we subtract from there and get our standard electrode potential. That's what this thing means. So we measure the tendency of an element to form ions in solution and compare it with the tendency of hydrogen atoms to form ions in solution, and then we get our standard electrode potential. Okay. The electrode potential of a given system depends on number one, the overall energy change. Number two, the concentration of ions in the solution, and number 3, the temperature. Now, it is not possible to measure the absolute value of an electrode potential directly. Instead, it must be measured against some reference standard. Remember what I explained? Now, hydrogen has been chosen. It's well known internationally. It's an international accepted standard that hydrogen is the arbitrary standard with an electrode potential of 0 at all temperatures. So if we say, okay, since the electrodes keep varying, electrons lost here, electron are less here, electron are more in the other one. Now let's decide one thing. Let's compare all of them to a particular electrode that does not vary, does not change. Okay, what is this electrode? Okay, let's choose hydrogen and say hydrogen has electrode potential of 0 at any temperature. Good, so that one does not vary then. Alright, let's compare others that keep varying with hydrogen electrode. Now that is how electrode potential is going to be measured. So the standard hydrogen electrode consists of hydrogen gas at 25 degrees Celsius and 1 atmosphere, those conditions, bubbling around an inert platinum electrode in contact with a 1 molar solution of hydrogen ions. Now if you go down to that diagram in that page where you see measuring standard electrode potential, that diagram, look to your right, you see that standard hydrogen electrode. You see that H2 hydrogen gas is bubbled in at 25 degrees Celsius and 1 atmosphere into that chamber, and you see a platinum electrode at the end there in contact with the water, in contact with the solution, right? You can see that, trace that in, and then the platinum electrode is what touches the electrolyte, so to say, the solution of the salt solution. So, but hydrogen is bubbled in, it's bubbling around the inert platinum electrode, and the inert platinum electrode is in contact with the solution, which is 1 molar concentration of hydrogen ions. So you see the setup in that part. The solution is hydrogen ion, then hydrogen gas is bubbled through into that space to meet the platinum electrode. Remember we said platinum behaves as inert electrode. It doesn't take part in that reaction, so it won't be choosing who I will discharge first, but that's not what we're doing right now. But you see the whole setup. Now that right hand side is the standard hydrogen electrode for this topic. So that's how it looks like. The standard hydrogen electrode consists of hydrogen gas at 25 degrees Celsius and 1 atmosphere, bubbling around an inert platinum electrode. Look at the diagram and you understand better. And the inert platinum electrode is in contact with the solution of hydrogen gas, which is with us a 1 mole concentration. Good. Now, how do you represent that electrode I'm showing you now in a equation? Go back to where the note is continuing. You see 2H plus in aqueous form slash H2 in gaseous form. That's the system. So you call it 2H plus aqueous. You put a slash H2 gas system. Now I will explain that. The 2H plus on the left hand side, you see, is in aqueous solution. It's aqueous, so it means it's in solution. It's in water. So it's referring to the 1 molar H plus solution which the platinum electrode is in contact with. That's the solution there in the beaker. But the other part of the slash, H2 in gas, is referring to the gas bubbling around the platinum electrode, and we couple that together to form a system. So that's why it's written system. So please don't forget, I'm not going to go back to be explaining that again. That's a standard hydrogen potential electrode used in measuring standard potential, standard electrode potential for any system. Okay, now the standard electrode potential of a given metal ions or metal system is then expressed in terms of the potential difference measured in volts which exists between the metallic electrode, the electrode of the metal, and the standard hydrogen electrode. So we are saying that you now measure the electrode potential of another metal, say zinc metal now. So by using that metal as material for the other electrode, since this hydrogen electrode is the one side, the other electrode is made with that metal we want to find electrode potential of, and then the salt solution of that same material made used for that other electrode on the other side. So if you look at that diagram, you see on the left hand side you see copper electrode, and the solution is what? Copper salt ions, copper salt solution, Cu2 plus 1 molar concentration. So you see copper electrode is used inside in a solution of copper salt, and this other way the standard electrode is used. So we are going to be comparing, you understand? So I'll read it again. The standard electrode potential of a given metal ion, like the copper in this other side now, stroke metal system, that's the metal ion is just like we said up there, 2H plus aqueous. The one in solution is the metal ion. The stroke here, I'll explain to you what that stroke mean. And the stroke there, and the other side is the metal system, H2 gas that was here. So this way it will be Cu2 plus. So if we want to write that system for this other left hand side of the diagram, it will read Cu2 plus aqueous stroke Cu solid system. Do you understand? Cu2 plus aqueous being the one in solution, just like we had 2H plus aqueous for that hydrogen equation written up there, and slash, we put the slash Cu gas or Cu solid, just like we had H2 gas on the right hand side, which is the metal system, and we add the word, it's a word system to show that that's the complete system. So I'll read it one more time. The standard electrode potential of a given metal ion stroke the metal system is then expressed in terms of the potential difference. So the potential difference that is measured in volts that exists between the metallic electrode, between the left hand side of that diagram, this copper electrode, and the standard hydrogen electrode, and the right hand side of that diagram, which is the hydrogen standard electrode. Good. Now the electrode potential value is positive if electrons flow from the hydrogen electrode to the metal electrode. Now you see that there is a salt bridge. There is a bridge that connects the two solutions together in that diagram. Now, and if you look at the platinum, the standard hydrogen electrode on the right hand side, you see that the cable, let's call it cable, or the line that goes from the platinum electrode goes into the voltmeter and then enters the copper electrode. The direction of the line is showing that it's going left. So, and if you want to follow that direction, you will see that the the electrons are flowing from hydrogen, the standard hydrogen electrode, to the copper metal electrode. So if this happens, you see the electrode potential value will be positive. So if you look at that diagram, you see up there where the voltmeter is, you see 0.34 volts. It's not negative 0.34, it's 0.34, it's positive. So the value, the electrode potential value is positive if electrons flow from hydrogen electrode as a standard electrode to the metal electrode, like the copper electrode on this diagram. But it is negative if electrons flow from the metal, like it flows from the copper electrode to the hydrogen electrode. So if the direction of flow in that diagram was flowing from copper electrode and going into the standard hydrogen electrode, then the voltmeter would be reading minus 0.34 volts. How do you know that it's the flow is going this way or going the other way? Because in reality you will not be seeing electrons moving and telling you I'm going this other direction. I'm telling you these figures now so that when you see minus 0.34, and you know, the electrons are flowing from the metal to the standard electrode, from the metal electrode to the standard electrode. But if you see a positive number, then you know, okay, so it's flowing from the standard electrode into the metal electrode. I hope you understand. Good. Now, the values of standard electrode potential are useful. How do you use those values when you see them? How do you use them? What does it stand for? Number one, we use them in predicting the direction or feasibility of a chemical reaction. Like I say, if you see that value is negative, you know, okay, it's moving from metal to standard electrode. But if it's moving from the other way around, you say, okay, it's moving. If it's positive, you know, it's moving the other way around. Number two is used in calculating the EMF of a cell. We are going to calculate that as we go on, and you will see. Number three is used in predicting the standard potential of unknown elements. Standard potential for known elements, like copper electrode in this diagram is unknown, but on the right hand side we know already the potential is 0. Of the standard electrode, potential is 0. So we use that to compare with this one, so we can be able to predict the standard potential of that one that is unknown. Good. So like play, we have already explained that diagram as it is. The only thing I've not really touched in that diagram is the salt bridge, but you are going to get full explanation on that salt bridge in due time, so I don't complicate issues. Now, from the apparatus above, the standard electrode potential of copper Cu2 plus stroke Cu solid system is being measured. So that's the diagram above, which we used in explanation, is a Cu2 plus stroke Cu system, Cu2 plus Cu stroke Cu system. We use that to measure this. We're measuring the standard electrode potential of copper metal dipped in a copper salt. Now, when the Cu2 plus stroke Cu system or half cell, that's the half cell, you know, it's two cells now, that's one half cell, is connected to the standard electrode potential, which is made of hydrogen, so it's 2H plus stroke H system, or the other half cell, by a salt bridge. So a salt bridge connects the two half cells. Take note. A salt bridge connects the two half cells together, so electrons can flow from this half cell to the other half cell through the salt bridge. Okay, so when they are connected by a salt bridge, the voltmeter shows a reading of 0.34 volts. That's because this is copper. So if it's another metal, it wouldn't be 0.34. Now this one does not need you to work out. You just connect. When you finish putting your connections in place, the voltmeter should give you a reading, and you can use that to calculate. Now the voltmeter should read 0.34 volts. If there was a standard, if you had a standard hydrogen electrode, hydrogen electrode on the right, on the one side, and the metal is copper, then it should read 0.34 volts. This is the potential difference between the two half cells. So 0.34 is the potential difference between these two half cells in the diagram, and this is known as the electromotive force of the cell. So remember calculating the EMF of the cell. So we have now known the EMF of that cell. That's not the last point. We'll still have to calculate. Now, the half cell reactions at the copper and hydrogen electrodes show that Electrons flow from the hydrogen electrode to the copper electrode. Remember the direction of flow. Hence, the electrode potential of copper is positive. That's plus 0.34 volts. When it shows positive sign, the voltmeter needle will deflect to the left, as to show it's positive. So the meter will be deflecting to the left. You know the needle is that stuff that looks like a watch clock handle. It should move to the left and read 0.34 and balance at 0.34. You know, okay, that's positive. That's how to read it. Don't look at left and say, oh, negative. Left should be negative things. Right is positive things. So when the voltmeter needle deflects to the left and rests on a particular number, then write out that number but put positive in front. So now at the platinum in hydrogen electrode, that is the standard hydrogen electrode, you know the platinum is inside the hydrogen ion, but at that electrode oxidation takes place where the hydrogen gas yields 2H plus 2E minus. That is the 2H plus in the solution gains 2 electrons, since it's 2 hydrogen, gains 2 electrons, and then becomes gain of it's you already know that gain of electron is reduction, but you are seeing oxidation in that note. Take notes. Let me quickly explain something before we move on so that we don't get confused. Now, we know that oxidation occurs at the anode and reduction occurs at the cathode, right? But in electrolytic cell, like we're doing in electrolysis, we say that the negative electrode is the cathode, while the positive electrode is the anode, right? Okay, now in this other electrode potential, when we're discussing electrode potential, that we'll be calling electrochemical cell, not electrolytic cell. So in electrochemical cell, the reverse is the case. The negative electrode is the anode, while the positive electrode is the cathode. So we see oxidation takes place at the anode, and oxidation is loss of electrons. So and we are saying that the negative electrode is the anode just for this electrode potential. So it means the anode has negative they have electrons, negative things there. So, and you know H plus was positive, so the 2H plus went to their anode and went to the anode and then got the 2 negative stuff there and was deposited. And you know in the anode oxidation takes place, so that's why it's oxidation here. In under electrolysis it would be reduction. So and it's H2 because you know hydrogen is diatomic. I don't have to remind you this again, so you have to include the 2 in the equation to show that hydrogen did not actually lose only 1 electron or gain only 1 electron. As shown in the diagram, you see it's H plus aqueous, 1 molar H plus. That's because in the ion it's not a gas yet. You understand that? But up there is a gas, right? Good. So as long as it's a gas, it's diatomic. So that's why the 2 is there. Now at the copper electrode, so the copper electrode now would be the cathode. The copper electrode, Cu2 plus 2E minus. So it had 2 plus also. Becomes 2E minus. Oh, sorry. It gained 2 electrons and then was deposited as solid copper. That's copper metal. And the overall reaction, if you want to add them together, you see, like we add the left hand side together and the other right hand side together. The other time, you remember, cancel out stuff from both sides. You will see that you have the equation Cu2 plus H2 yielding Cu plus 2H plus. Alright, if you have gotten that, it means you really understood balancing of redox equations. Alright, now there is a table there for the standard electrode potentials of some common metals. So if you are coupling potassium K plus and its salt and the metal itself K plus and K plus stroke K system with the standard electrode potential. You're coupling that with hydrogen. The voltmeter should read minus 2.92 volts. If you are doing that, if you are using calcium salt, if you are dipping calcium metal into calcium salt, coupled and you are comparing that with a standard hydrogen electrode, you should have minus 2.87 volts. If it's that for sodium, you should have minus 2.71. If it's that for zinc, it should be minus 0.76. If you're coupling hydrogen against hydrogen, hydrogen is 0.00. You cannot couple hydrogen against hydrogen. Hydrogen is already known, it's 0. And Cu2 plus, after being coupled, it should read plus 0.34. Ag silver should read 0.80. Gold Au should read 1.64 volts. So that's just a table to show you the standard electrode potentials of some important metals you would be needing. Now, I have explained this electrode potential the way it is in your notes, the way it is in my notes I gave to you. But I want to explain it in a different way now. So you have to listen very attentively because this, what I want to explain, is not in your notes, but it will give you a better insight of the topic. Okay, firstly, you can't tell which electrode is positive or negative until you connect a voltmeter. I'll tell you why I'm saying this. When we're defining electrode potential, we said that the reduced and the oxidized form of the metal come in contact. And this we are saying is at a particular electrode, just one electrode, we see the reduced and the oxidized ions coming together. And I tell you what, they react, and oxidation and reduction can even take place there. So if oxidation and reduction can take place there, you don't really know where oxidation takes place or reduction takes place. But I'm going to explain it somehow different so that you understand this point. But before then, the standard hydrogen electrode is a redox electrode. When we say redox, reduction and oxidation takes place. So the standard hydrogen electrode is itself is a redox electrode. It forms a basis of oxidation reduction potentials. So it's the reason why I'm saying that you can't actually tell which one is negative or positive electrode until a voltmeter is attached or connected. Now, as the hydrogen gas flows over the platinum, it's platinum in hydrogen electrode, that's the standard hydrogen electrode, an equilibrium is set up between hydrogen molecules and hydrogen ions. Hydrogen molecules are neutral. They are metals. They are neutral atoms. They don't carry positive charge, they don't carry negative charge, right? Because they are neutral. And the ions they are dipped into are positive. So we're having neutral electrode in a positive ion substance, so to say. Now, that the hydrogen rod will react in the solution, and reduction can take place, oxidation. But let's not look at that. But generally, as the hydrogen gas flows over the platinum, the equilibrium is set up between hydrogen molecules and hydrogen ions in the solution. So the reaction is catalyzed by the platinum there. Once again, remember, platinum is inert. It does not concern itself with the reaction. It just serves as a surface for electricity to pass through. Okay, now I'm going to explain electrode potential all over again, but in a different way. In fact, I will need you to listen to this audio and write it out one by one. It would really show that you get what I'm saying. But listen, when metals react, they lose electrons and form positive ions, right? Remember, when the metals react, they will lose the electrons. When you lose negative things, you become more positive, right? So they lose electrons and form positive ions. Electrode potential deals with the ease with which these metals lose electrons to form ions in solution. So this topic is just dealing with how easy is it for a particular metal to lose electrons so that it could form ions in solution. We're going to use two metals to discuss this short explanation: magnesium and copper, Mg2 plus and Cu2 plus. So we'll discuss them one by one. Now, remember, magnesium is more reactive than copper. You remember your periodic table, electronegativity and reactivity and all those one, the trend. You can go back and read that. So, but magnesium is more reactive than copper. So, because magnesium is more reactive than copper, magnesium will easily react to go into solution than copper can. Because of this, magnesium will have a greater potential, but we'll see how that happens. So this electrode potential topic stuff is just trying to express this ease of these metals to lose electrons and form ions. Just trying to attach some numbers to the ease, a value. Say, okay, the ease of losing electrons of this one is 2 point this. So this whole topic is just trying to attach values to how easy it is for different elements to lose electrons and form ions. You understand that? Let's go. Supposing you have a magnesium electrode inside water. Just dip only magnesium electrode inside water. So what magnesium electrode can be any rod made of magnesium. Just dip it into water. Now, what will happen is this. Magnesium atoms, which you know, magnesium when its atom is neutral, any metal when its atom means it's neutral, not carrying negative sign, not carrying positive sign, they are neutral. So magnesium atoms will dissolve into solution. Now, when it dissolves into solutions, it's forming ions, because when you dissolve, it means you have ionized. Now it's now ion, and ion will carry a charge. So it's what happened is that when it dissolved into solution, magnesium left behind negative stuff. It left electrons on the rod, and then dissolved into the solution, the water. When you are leaving behind negative things, what will you have? You'll be having positive. You'll be having positive, more positive. You'll be more positive. So when magnesium atom dissolves in the solution, it leaves behind electrons on the electrode. So it becomes more positive. So that's why you see Mg2 plus in the water, and the electrode is now more negative now, because 2 electrons have been left there, and then it becomes 2 plus inside the water. You understand that? Just imagine what I'm saying, because it's not in your notes, no diagram. Now, all the magnesium atoms on the electrode, one by one, they will be dropping electrons like that, dropping to 2 electrons. and they will become dissolved into solution until there will come a point where the magnesium electrode has so much electrons, and if the magnesium electrode has so much electrons, it means the water will have so much of the positive ions, right? So the water will have so much Mg2 plus, and the rod, the magnesium electrode, will be left with negative, 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 just electrodes, because these atoms in magnesium were just leaving the magnesium. When you leave, you have to drop your electrons there before you become positive. Inside the water, you form positive ions there. So they deposited their two electrons each as they were going into solution. So the electrode becomes filled with electrons. The solution now is filled with positive charges, Mg2 plus, Mg2 plus, Mg2 plus. You understand that? Okay. Now, when this happens, they form. There will be a layer. It will be a different, since negative and positive now, the rod is negative, the water is filled with positive ions. At the boundaries of the rod, there will be a layer that tries to separate both of them, because they are not the same. This one is neutral, the other one is positive. You understand? The rod is neutral, but it has electrons in them. But this layer will be formed surrounding the electrode. Now, this layer will be very close to the electrode because it contains positive ions which are attracted by the negative electrons on the electrode. So the layer will not be so far apart from the electrode. It will be very close because it has positive things and the electrode has negative things. They are attracting each other. They want to join. But joining does not just happen. It has to gain the electron again and become associated with the rod, the electrode. So now some of these positive ions in the water will be attracted so much that they will reclaim the electrons. They will gain back the electrons they deposited on that electrode and stick back to the electrode. So the one that was the atom that was detached because it went into solution will come back and then get back the electron it deposited and get attached again to the electrode. Now, this will keep happening. It's not like when it reaches there, it will now stop. That one has completed a cycle. No, it will keep going back into solution and then coming back again. So you see that cycle. But at a point, the rate at which ions are leaving the electrode will be exactly equal to the rate at which the ions are rejoining the electrode. You understand that? So when that happens, we say there is a dynamic equilibrium. So a dynamic equilibrium is established. I've explained this before, so I'm just putting it somewhere else. Now, this means you will be having a constant negative charge on the magnesium electrode and a constant number of positive magnesium ions in the solution, right? Because we're saying there's a dynamic equilibrium. The same number of ions leaving the electrode are equal to the number of ions rejoining the electrode. So you'll be having the same number of ions in the water being equal to the same number of ions in the electron in the electrode. So this will become constant because they are equal. Now, that is for magnesium. Now, how would this be different if copper was used? Now, copper is less reactive than magnesium. It's not as reactive as magnesium. How does this affect what we're saying? So, since it's less reactive, it does not readily form ions. You see, magnesium, once the rod was dipped in, because it's more reactive, it easily goes into solution and come back and goes in, you understand? So it's easy for it to run up and down. because it's more reactive, but copper is not as reactive as that. So it takes difficulty for copper electrode now to dissolve and form ions. So any ions which do even break away from the copper electrode, they are more likely to come back and reclaim their electrons and sit back on the metal again, because it's difficult for them to go back to go into ions, but they will still go back. But you will still reach an equilibrium, but there will be less charge on the metal. And since there is less charge on the metal, there will be fewer ions in the solution. You understand that, because the number of ions that left the metal, the copper metal now, was not much. So there are few number of ions in the solution. And since the number of ions that left the metals are not much, it means not much of electrons are deposited on the copper. So you'll be having less electrons, less negative charge on the metal, and few positive ions in the solution. So if we compare those two, the magnesium and copper, we say that generally, if you want to know the ease with which these two metals, that's magnesium and copper, dissolve into ions, then we will have to compare the two positions of equilibrium when they meet, when they attain their equilibrium. We have to compare those two positions. So this comparison of the two positions is what potential electrode potential is all about. Everything else concerning electrode potential is just an attempt to attach numbers to these different positions of equilibrium. Okay. So, in the case of magnesium, there is a lot of difference between the negativeness of the metal and the positiveness of the solution. You know, there are much electrons on the electrode, the magnesium electrode. So there is a lot of negativeness on the metal, and there is a lot of positive ions in the solution. So there is a lot of positiveness in the solution. So you have a difference between the negativeness of the metal and the positiveness of the solution around it would be much. Whereas in the copper, when you're using copper, the difference is much less. You understand that? So it is this potential difference, that is recorded as voltage. So the bigger the difference between the positiveness and the negativeness, the bigger the voltage. But unfortunately, this voltage is impossible to measure. You can't just measure this voltage using that one electrode. One electrode is there, just one rod is there, because if you connect the voltmeter to the metal, you will need to connect the other end somewhere else, negative and positive wires. So, and if you connect the other end into the same solution, they will both have a similar equilibrium, right? So you can't really measure the potential difference using voltmeter there. Now, listen to this. If we have a pole of fixed height, we know the height of the pole. Say it's maybe we don't actually know the height of the pole, but we know that it's fixed. It's not moved. It's mounted on the ground. So that height that pole has, we cannot shift it. That's a fixed height now. And we have three boys. They have different heights. Now, we can use that fixed length of pole to measure the height of those three boys, right? Now, how can we do that? Now, if a boy is 15 cm taller than the pole, we record, okay, this boy is plus 15. You understand that? The one that is 20 centimeters taller than the pole, we record, okay, Emmanuel is plus 20. John was plus 15. All right, and the one that is 15 cm shorter than the pole, How do we record it? Minus 15. So we say, okay, mass is minus 15. The girl now. Alright, so if we can do that, then that is the same way the standard hydrogen electrode is used to measure the potential difference of metals like this magnesium and copper metals. So when the platinum electrode attains equilibrium, and the standard platinum in hydrogen electrode attain equilibrium too, so now we are using the magnesium with the standard platinum electrode, standard hydrogen electrode, which is platinum in hydrogen electrode. So we want to use that as the pole now to measure height with this Marcel, John, and Emmanuel. So now we are using the pole to measure with Marcel. We use the pole and measure with John differently now, but the pole is always measuring with one person. So now we are using the pole now, which is in this case the standard hydrogen electrode, and we're measuring it with the magnesium electrode. So when the magnesium electrode attains equilibrium, the reaction there has attained equilibrium, like it was explained before, and then that of this standard hydrogen also attains equilibrium. Now there will be a much greater buildup of electrons on the magnesium. Since magnesium is more reactive than hydrogen, which is used on the other side. Magnesium will have much more buildup of electrons on the electrode, on the metal, and the magnesium metal than on the hydrogen, and that's the platinum electrode. Now this difference can be measured using a voltmeter. Now we have two poles to be able to connect. So if we connect a voltmeter, the voltmeter will read 2.37 volts. That means that the potential difference measured, set up between those two equilibrium is 2.37, and we know that we've already known that hydrogen is 0. So if we find a difference, 2.37 minus 0, we still have 2.73. Okay, so it means we call that magnesium has 2.73 volts. Now, but this voltmeter would show that magnesium is the negative electrode, and that the hydrogen is the positive electrode. Now the voltmeter is now deciding which one is negative electrode and which one is positive electrode. Now in another case, hydrogen can become the negative. We'll see that. So you understand why I said you cannot actually know which one is the negative electrode or which one is positive until a voltmeter is attached. Okay, so now you remember we said if the voltmeter reads negative, then you know that the electron is flowing from the metal to hydrogen. But if it reads positive, then you know it's flowing the other way around. I might mix it up, but you remember what we're saying. Now this voltmeter will show that magnesium is negative electrode, and that the hydrogen is the positive electrode. But this is because the magnesium has a greater amount of negativeness, since it's more reactive than the other hydrogen electrode. It gathers more electron because it easily goes into solution, and then electrons are left behind on the electrode more than that of hydrogen, because this one is more reactive. Now, so since magnesium has more negativeness, so more electrons, then the voltmeter records that as negative. And the platinum in hydrogen electrode, that is standard electrode, is not as negative as magnesium, even if it's negative, but not as negative as magnesium means that it is more positive than magnesium, right? Okay, we are saying it is more positive, so the voltmeter records it as positive. You understand how the trick is done now, that the voltmeter will be reading this and reading that. Okay, now just for a little calculation, you know that plus 0.4 is more negative than plus 1.2, right? Good. So on the other hand, we can say that minus 0.3 is relatively more positive than minus 0.9. So that's the way the voltmeter does the negative and positive recording. The one that is more has more electrons, take the negative. The one that has more electrons than the other has, take the negative, and the other one has to be positive, even if it is negative, or it can change in another reaction. Now, let's take for instance, we replace the magnesium electrode with the copper electrode. Remember, we are still using copper and magnesium. If we replace the magnesium with copper, so we have copper in the salt of copper solution. We have copper rod in the salt of copper solution now, and the other side is standard electrode, which is hydrogen electrode. Now, in this case, copper is slightly less reactive than hydrogen. The other one, magnesium, was more reactive than hydrogen. But in this case, hydrogen is more reactive because copper is not as reactive as hydrogen. So there will be less buildup of electrons on the copper. The copper will not have a lot of electrons compared to that of hydrogen, because hydrogen is more reactive than copper in this case now. So since it is a slight difference, copper is slightly less reactive, so it's not as if it's as big as magnesium was with hydrogen. Copper is not as big. There is no big difference like that. Hydrogen is just slightly more reactive than copper. So because this is a slight difference, the voltmeter will detect that there is a slight difference between the electrical charges on the two electrodes. So when it does that, the voltmeter measures it and reads 0.34 volts. So 0.34 volts is not as big as the difference between 2.37. You understand? So this one is still in the range of 0. Since hydrogen is 0.00, but copper is showing 0.34 volts. Now, since hydrogen is more reactive than copper, hence more buildup of electrons on the hydrogen electrode than the copper electrode, the voltmeter will record copper as the positive electrode, since it has the less negative electrode. It is the less negative electrode, sorry, and it will record hydrogen electrode as the positive one, being more negative than copper. So you see that now in this case, when copper is coupled with hydrogen now, hydrogen becomes the negative electrode, but when it was coupled with magnesium, hydrogen was the positive electrode. So you now agree with me that you can't really decide which electrode is positive or negative until you attach a voltmeter. Now, we know what happens in the two electrodes, the standard electrode and the metal electrode, as the two half cells. And let's see how we can bring in these two half cells and the two half cells together, not necessarily now with the standard electrode, since we can measure them out already. We have values of what these electrodes are. So it's when we want to measure the electrode potential of a particular electrode or metal that you have to couple it with and compare it with hydrogen. Now that the values are already known, you can go ahead and compare put in two different metals side by side, as the two different electrodes, and then you measure out your difference in electrode potentials. Remember, we said it's used in calculating EMF of a cell. Good. So that's that point we are right now. So we are considering electrochemical cells. Electrochemical cell is defined as a device or a cell, simply, which converts chemical energy to electrical energy. So those are ions in the solution, so they are chemicals. Now the electrochemical cell can convert the energy in that the chemical energy into electrical energy. you practically see electricity. You see light. If you connect a bulb in place of that voltmeter, you see light shines because electrons are flowing. So electrochemical cell is a device or a cell which converts chemical energy to electrical energy. Now, an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy is known as a galvanic or voltaic cell. Now, when we mention spontaneous reaction, a spontaneous reaction is a reaction that will take place by itself. It doesn't need an extra force for it to take place. So on the other side, a non-spontaneous reaction is a reaction which would need extra energy for it to happen. So a spontaneous reaction will happen on its own accord. You don't need to force it. So electrochemical cells that converts chemical energy of a spontaneous redox reaction into electrical energy is known as a galvanic or voltaic cell. This is the one that is most important to us because we don't need to force the reaction. Now, these electrochemical cells achieve this conversion by harnessing the energy produced by the redox reactions that occur within the cell. You know, we say reduction and oxidation occur inside the cell. So it will harness the energy produced by that reaction and use it to produce electric current. Now, a galvanic cell consists of two half cells. An oxidation half cell reaction occurs at the electrode in one half cell. You're already familiar with that. And a reduction half cell reaction occurs at the electrode in the other half cell. And so if you combine the two, the overall reaction will result in a flow of electrons. And when electrons are flowing, you say electric current is seen or is felt. Now, so that you will not confuse yourself with electrolytic cell and electrochemical cell, you can go back and read what electrolytic cell is. The assembly of two electrodes in an electrolyte. You understand? You remember? That's in electrolysis. But electrochemical cell is just a device that converts chemical energy to electrical energy. So note that difference. But let's see the similarity and the differences. In both cells, in both electrolytic cell and electrochemical cell, oxidation always occur at the anode, and so conversely reduction will occur at the cathode. And also electrons always flow from the anode to the cathode. Electrons will flow from the anode down to the cathode in both electrolytic cell and electrochemical cell. But what are the differences? One, in an electrochemical cell, the negative electrode is the anode, while the positive electrode is the cathode. That's as opposed to electrolytic cell. You know, in electrolytic cell, the negative electrode is the cathode, but in electrochemical cell, the negative electrode is the anode, as I explained. So that's the difference between electrolytic cell and electrochemical cell. Now, let's look at this salt bridge. Remember I said that we'll deal well with salt bridge when it's time. Now, salt bridge. A salt bridge is a tube filled with a weak electrolyte. Take note, weak electrolyte, which serves as a connection between the oxidation and the reduction half cells in a galvanic cell. So the galvanic cell is made up of two half cells, the oxidation half cell and the reduction half cell. This is different from the standard electrode cell, which you don't actually know which one is negative or positive actually. This one, there is a reduction half cell, there is an oxidation half cell. So those two cells are apart. It's not that they are together. This one is in one beaker, the other one is in another beaker. So they are apart. The solutions are not mixed together like in electrolysis, where the electrolytes are in one place and the two electrodes are immersed in the same electrolyte. No, this one solution is different and the other one differently in two beakers. So how do we connect the two together? Using a salt bridge. So A salt bridge is a tube filled with a weak electrolyte. Of course, when we say electrolyte, you already know it's in a solution, which serves as a connection between the oxidation and the reduction half cells in a galvanic cell. So its purpose is to keep the electrochemical reaction from reaching equilibrium too quickly. I will explain this a little later, how it stops the reaction from reaching equilibrium so quickly. I will explain that, but take note of this. A piece of filter paper, in case you don't have a glass tube, a piece of filter paper soaked in sodium chloride or in potassium chloride or in ammonium trioxynitrate 5 solution can serve as a salt bridge. You can use that as a salt bridge. But let me explain what salt bridge really, how it really happens. Now, the two half cells are there. The salt bridge is included to complete this electric circuit. You know, the two half cells is connected with a voltmeter the other way. You understand? Possibly. So the rod goes when what connects the oxidation half reaction with the reduction half reaction only without the salt bridge is that just the wire what will transfer what carries the electricity into the electrolyte. Good. So, but nothing connects the other parts. You know, the circle is not complete, so electrons will not flow accurately. It will not even flow. It will just be testing the electrolytes, but we need a flow of electrons. So the salt bridge is just included to complete the electrical circuits. But you know, we don't want to introduce another metal. You know, the oxidation half cell already has its metal there and its metallic ions inside the solution, and the reduction also has its own metal and the solution there. If the salt bridge is made of metal, it's made of another metal, introducing it there will, you know, be adding bits of some metals into the system, extra metals into the system, and maybe even different metal, which will start another process, you know. So we don't need that. So we have to use a material that is inert, does not react. So that's why it's a glass tube that is used. Glass does not react. Yes. So it's just a glass tube that is filled with weak electrolytes. Now, but these glass tubes are open at both ends, so it's bent but open at both ends. So electrons, the solution will enter from this tube and can meet with the electrolytes inside the tube. You understand? So now let me explain how the salt bridge helps stop the equilibrium from reaching too quickly. Now the both ends of the salt bridge, which is a glass tube, they are fitted with cotton wool. The reason why it's fitted with cotton wool will only soak up what is inside the glass tube, and what is outside the glass tube, which the glass tube is now immersed in the liquid. If you look at that diagram I was using to explain, the glass tube is the salt bridge, which is the glass tube, is immersed into the solution at both ends, but the glass tube inside has another different electrolytes, different from the ones that are in the two half cells. So now we don't want the electrolytes inside the glass tube to just react with the one inside just fast like that, just drops in and reacts. So fixing cotton wool at both ends will, the electrolyte inside has to soak up the cotton wool, so it will be dropping slowly into the solution at both ends. So because they will be dropping slowly, they will be stopping too much mixing of the contents of the salt bridge with the contents of the two beakers. You understand that? So that's how the salt bridge helps stop the two half cells from reaching equilibrium too fast. So now the electrolytes also used in the salt bridge is chosen so that it does not react with the content of either beaker. So if you're using magnesium on the other beaker and using copper on the other beaker, you don't choose an electrolyte that is copper or magnesium, a different thing, so that it will not be reacting with the content. So just understand that you don't choose an electrolyte that will be reacting. That's why it's a weak electrolyte we're choosing. Okay, now what are the functions of a salt bridge? In case you're asked in exams, though I've explained them, but this is what you're expected to write. Number one, it allows electrical contact between two solutions. You know that it completes the electric circuit. That's how it allows the electrical contact between the two solutions. Number two, it maintains electrical neutrality in each half cell. So that is it allows the cations from the other electrode and the anions from the other one to move from one electrode compartment in one beaker to the other. So the salt bridge moves, but just that we don't want it to move so fast, so we insert cotton wools at both ends, so that you have to go slowly, but they will still mix up, they will still pass. So those are the functions of salt bridge. Now, there are so many possible galvanic cells. So there is a shorthand notation to describe or provide information about the various species involved in the reaction. The reaction are going to be the same, but maybe a different construction, but the same kind of reaction will take place. So if you look down in your notes, you see number one, a vertical line. When you see one slash, sometimes in exams you will see vertical line instead of slash, but when it's just one, it can either be a slash or just a vertical line. But when it's just one slash or one vertical line, it means a phase boundary. Phase, P-H-A-S-E, phase boundary. Now when we say a metal is dipped into a solution of that its salt, the metal salt, what is the metal? The metal is the solid form. So if we are using copper, like example there in that your note, Cu in solid form, that solid form is the phase. So solid, liquid, you can have a liquid, you can have aqueous, those are phases, phase. So the solid form is the phase, is the one phase, and the Cu2 plus, which are ions now, they are in the solution. They are aqueous now, so that's another phase. So using one line, you see in that example I used one line to mean that that's just a phase boundary, a boundary between the two phases, boundary between the electrode and the solution. Good. Number two, when it's a double line, double vertical line, or double slashes, as the case may be, it means salt bridge. So if you see one line, it means phase boundary. If you see two lines, it means salt bridge. I will have to show you somewhere so that you understand better. But take note, the information about the anode is written to the left always. If you keep to that, then you will understand better how the electrons are deposited. The information about the anode should be written to the left, while the information about the cathode should be written to the right, and so that a salt bridge will come in between them. Good. You will see that as we calculate actually. Alright, so remember we said we can use the values of the electrode potential to calculate EMF. Good. Now we are calculating the EMF of a cell. Now EMF of a cell is equal to the electrode potential of the cathode minus the electrode potential of the anode. So we can say E cell equal to electrode potential of the right hand side, since we said that the information about the cathode is written to the right and the information about the anode is written to the left. So if EMF of the cell is electrode potential of the cathode, which is written on the right, minus the electrode potential of the anode, which is written on the left, then we can say that EMF of a cell is equal to electrode potential of the right hand side minus electrode potential of the left hand side. So or we just simply say EMF of a cell equals to E cathode minus E anode. Good. So it's the same thing. Now we see this example. Given the electrode potential of copper to be plus 0.34 volts and that of zinc to be minus 0.76 volts, calculate the EMF of the cell. It's quite very simple. So you just bring down your formula. It says electrode EMF of a cell equal to E cathode minus E anode. Now the question gives you that the electrode potential of copper is plus 0.34 volts and that of zinc is 0.76. Now remember in the differences we said that in electrochemical cells the negative electrode is the anode. So in that question, the figure that the value that is negative minus 0.76 V means that's the negative electrode, which is the anode this time around now. So that's the zinc is the anode then. So it's going to be on the right. So it means the other one, copper, is going to be the cathode. So E cathode minus E anode will become E copper minus E zinc. So you just bring down the values. Plus 0.34 minus 0.76, that becomes positive 1.10 volts. So that's the EMF setup, the EMF of the cell. If copper, the cathode was copper and the anode was zinc. Now take note of this. When a cell has a positive EMF, like that example we just solved, is a positive EMF plus 1.10 volts. It means that the system is spontaneous. It means the system it happens on its own accord, doesn't need extra force or energy. But if it is negative, it is non-spontaneous, meaning that the anode will not be able to reduce the cathode. It cannot happen on its own accord, so something has to be used, but we don't want to go there. So a bit of a reminder: a spontaneous reaction is a reaction that occurs without intervention. You don't need to force it, or simply a reaction that will tend to happen. It will happen. Nothing will stop it from happening. Example: you see a ball rolling downhill is spontaneous because it will tend to happen without intervention. Nobody has to push it because it's going to be rolling down the hill. It doesn't need extra energy. It just goes down. But if a process is not spontaneous, then it will tend not to happen, except some external forces applied to make it happen. Like if we say, let that ball return back to the top of the hill, return to the top of the hill where it came from, it can't just roll up there. It's not spontaneous anymore. It can't happen on its own accord. Someone has to carry it there. Yeah, so that's the extra energy added. Now, if the standard change in free energy, Gibbs energy, is negative, so if you have negative Gibbs energy at a given temperature, then the reaction is spontaneous. So, since you don't need to add any energy, since you're not adding, so it's negative. You don't need to add any energy to make spontaneous reactions occur. So since you're not adding any energy, adding energy means positive. So since you're not adding, which is positive, then it is negative. So when you have negative Gibbs energy, you should just know that reaction is spontaneous. But if the Gibbs energy is positive, then it's non-spontaneous because we had to add that energy, add Gibbs energy to make the reaction occur. Now, what are the types of electrochemical cells? Now, electrochemical cells are widely used, employed to generate small currents of electricity for everyday use and industrial operations. But electrochemical cells are classified into two main classes. So we have the primary cells and the secondary cells. So we are going to, in brief, look at the difference between a primary cell and a secondary cell. A primary cell cannot be recharged, whereas a secondary cell can be recharged. Take note, we'll mention some examples and then you will understand how. Primary cells do not last long. Since it cannot be recharged, it means when that power gets finished, that's all. But secondary cells last long. Now, reactions in primary cells are not reversible. You know, when you say reversible reactions, you have the two arrows at the center, not facing one side now. The one can go the other way and it can reverse. So, reversible reactions now. So, primary cells, the reactions are reversible, whereas in secondary cells, reactions are not reversible. But then some examples of primary cells are Daniell cell, Leclanche cell, dry cell, radio battery. Radio battery, when it dies off, you don't recharge it, do you? No. Alkaline battery, button battery, those batteries, small battery you put in a wristwatch, button battery and all those. Touch battery, clock battery, when it gets exhausted, the power is gone, you don't go and recharge it, you throw it away, buy a new one. Bicycle lamp battery and the rest. So, but in the secondary cells, which can be recharged, lead accumulator, lithium ion battery in rechargeable lamp. Of course, you're already hearing rechargeable lamp. Since it's a rechargeable lamp, it can be recharged, the battery can be recharged. Car battery, car battery, you can use one car battery for years. So that battery is recharged when you're driving, when your car is steaming, so it's rechargeable. Nickel metal hydride cell, phone battery, of course, that one we charge it a lot, so it's an example of secondary cell. Nickel cadmium cell, hydrogen oxygen fuel cell, aluminum air battery, and so many others. Now, there are some we're going to break down and explain. So we're going to pick Daniell cell from the primary cells, Daniell cell and the Leclanche cell from the primary cells, and then we'll take lead accumulator from the secondary cell and discuss. So briefly, let's go. Daniell cell consists of a copper vessel, so the container is made of copper, filled with a saturated solution of copper 2-tetraoxosulfate 6 and a porous pot filled with a zinc tetraoxosulfate 6 solution. So you see metal and the salt, solution of its salt. Now, a zinc rod is immersed in the zinc tetraoxosulfate solution. The initial EMF produced by the Daniell cell is about 1.1 volts. Now, this cell has to be replaced once the chemicals in it is depleted. It's a primary cell, cannot be recharged, so you just have to replace the cell. Okay. Now, the Leclanche cell, the anode and the cathode are a zinc rod. So the anode is a zinc rod and the cathode is a carbon rod. Now, the electrolyte, the solution now, is an ammonium chloride solution. That is if the cell is the wet cell, or you have ammonium chloride paste if it's in the dry cell, but it's ammonium chloride. Now, Leclanche dry cell is the most common cell used in many small electrical appliances such as touch is what you call touch lights, touches, or touch, radio and bicycle lamps. Now for the secondary cell example, lead accumulator. Lead accumulator is commonly used as a car battery. So it is a secondary or storage cell, so you can call secondary cell storage cell, as it must be charged by passing a direct current through it. Remember, it's a direct current, DC. The cathode of a fully charged lead accumulator is lead 4 oxide, and its anode is metallic lead. So the electrolyte is, so what you should pick is what is the cathode material, what is the anode material, then what is the electrolyte. So the electrolyte is a dilute tetraoxosulfate 6 acid solution. That's H2SO4. Now, when the two electrodes of the lead accumulator are connected to an external circuit, it produces electricity by discharging the battery, and the current draining out from the battery is used to produce the electricity. That's what we call discharging. Now, in the assignment section, when you want to do your assignments, you are to tell me how the lead accumulator can be charged back. This is discharging now. It's using the current it has to produce electricity. How can we charge it back? Now, take note. You will use your textbook. When you get to where this lead accumulator is in your textbook, you can see all that is in your assignments there. That's just a little hint, so you can use that to do your assignments. Now let's get to conductors and insulators. Conductors and insulators. Now, substances which conduct electricity are called conductors, right? But they are of two types. Metallic conductors on one side. As example, metal wires, graphite, which is an electrode of carbon, which can conduct electricity, and then mercury conduct electricity by movement of electrons. They are metals, so electrons have to move on them. Now, we have on the other hand electrolytic conductors. That's electrolyte. This one is in solution now. Example, we have fused lead 2 bromide. Fused, when it's fused, it means lead is fused with bromine, so it contains lead and bromide ions, so they are joined together, fused together. It's a compound. We have sodium chloride solution and dilute hydrochloric acid. Now, all these in solution, they can still conduct electricity. That was what we used in electrolysis. You remember that. Now, how about the ones that don't conduct electricity? Non-conductors, or we call them insulators, are substances that do not conduct electricity. They are either pure solids. Pure solids don't conduct electricity because they don't carry any charge. Remember, pure. When you say pure, when it's a metal is pure. Sorry, I'm using pure now. When a metal is free, then we say it's neutral. But now, when the solids are pure, they don't contain electrons, so they can't conduct electricity. Or if they are liquids that are not electrolytes, remember we say electrolytes must conduct electricity. If they are liquids that are not electrolytes, then they will not conduct electricity. And those ones that don't conduct electricity, we call them insulators. Like you see your rubber don't have electrons, but it's a solid. It doesn't have electrons in them, so they don't conduct electricity. If you put them in between two terminals, negative and positive, it simply stops the current from passing through. So because it's an insulator, it doesn't allow current to pass through it. Now, let's briefly look at this classwork. It's supposed to be a classwork if we were together. So let's still do it together. Number 1. A standard galvanic cell constructed with Ag plus aqueous, Ag solid. There should be and zinc 2 plus couple is discharged until 3.3 gram of Ag forms. Now, number 1, write the overall cell reaction and standard cell potential. How many moles of electrons flow through the circuit during the discharge? And then the last one, how many columns of charges flow through the circuits? Now the equations are given there. Ag had only one positive ion, so it has to gain one electron to become deposited as neutral Ag. So it's solid now, that is neutral. And zinc had 2, so it has to gain 2 electrons to become deposited as neutral zinc metal there. And when Ag was reacting, the EMF was plus 0.80 volts, while when that of zinc was minus 0.76 volts. And the mass of Ag, molar mass of silver Ag is 108. So let's use that to solve. Now we're asked for overall reaction, and then we see that overall reaction means you have to add the two half equations. You remember how we used to add those stuff. Oh, now remember, in this second that equation of zinc. Remember when I said since it's 2 plus, it loses 2 electrons. Now, if it's losing 2 electrons, it forms in this other, when we are writing overall reaction, you see it's 2 Ag plus zinc. Now, since on the right hand side zinc is 2 plus, it means that this zinc on this left hand side lost 2 electrons, isn't it? Or gained 2 electrons. Now, since it gains 2 electrons, to balance that up, it means Ag, all also would lose 2 electrons. So just a balanced equation. Or simply, so that there will be no confusion, just ignore the 2. So just read Ag plus zinc reproduces Ag plus zinc 2 plus, but that's odd, so think about the 2 plus. Okay, so now the cell potential, the EMF is E cathode minus E anode, and we're given a negative figure for zinc, so zinc becomes the anode. So plus 0.80 minus 0.76, we add that up and we have plus 1.56 volts. So that's the overall cell potential. Now the second one, how many moles of electrons flow through the circuit during the discharge? Since Ag had 1 positive charge from the equation, first equation given in the equation, plus, so it had to gain 1 electron and became deposited as neutral Ag, and the molar mass of Ag is 108 grams. So it means 108 grams of Ag is 1 mole of electron, since Ag is just 1. So 3.3, which is the gram of Ag in the equation, will be equal to, just like we're doing in electrolysis, 3.3 times 1, since it's 1 mole, all over 108. Don't confuse this with the other one, with electrolysis, but almost the same thing. So 108 is the mass that will be going down now. So 3.3 times 1 mole all over 108 equals to 0.03 moles. So that is the number of moles of electron that was flowing. But the III says how many columns of charges flow through the circuit. Now, but if 1 mole is equal to 96,500 columns from electrolysis, right? Then how many columns will 0.03 mole of electrons be? So simply that would be, if you use 96,500 columns as your reference point, so 0.03 mole will be 96,500 times 0.03. So you will have 2,895 columns. So 2,895 columns, or 2.89 times 10 raised to power 3 columns, is the amount of columns of charges that flow through the circuit. Just follow the examples carefully, and then you will understand. Alright, so we have come to the end of the topic electrode potential. Do well to drop your questions on the group and do your assignments. For more clarification, you need that textbook you have to do the assignments, especially the part that says explain what happened at the cathode and anode of a lead accumulator when discharging, and explain how a lead accumulator is recharged. And also number 3, which says explain why corrosion is an electrochemical process, and explain how to prevent corrosion by cathodic protection. All those is just in those pages where you see lead accumulator. So thank you for the time. I need you to listen over and over to this record until you understand perfectly and you can teach others. And until our next class, stay safe. God bless you.